19.6 Energy Transfer Mechanisms in Thermal Processes. In this session, we will explore the different ways energy moves during thermal processes. Our discussion will cover three primary mechanisms: thermal conduction, convection, and electromagnetic radiation. We will also look at how these principles are applied in practical ways, such as in-home insulation and the design of the Dedoir flask, which many of you know as a thermos. Let us begin with thermal conduction. This is the transfer of energy by heat through atomic scale exchanges of kinetic energy. On a microscopic level, particles with less energy gain more by colliding with their more energetic neighbors. In metals, this process is particularly efficient because it happens through both the vibration of atoms and the motion of free electrons. Because these free electrons can transport energy over large distances, metals serve as excellent conductors of both heat and electricity. The law of thermal conduction states that energy transfer requires a temperature difference between two regions. Imagine a slab of material with a specific cross-sectional area and thickness. The energy transferred over a certain time interval is equal to the thermal conductivity of the material multiplied by the area and the temperature difference, all divided by the thickness of the slab. We can also express this as power, where the rate of energy transfer equals the thermal conductivity times the area, multiplied by the magnitude of the temperature gradient. The diagram here shows energy flowing from a hotter face at temperature TH to a colder face at temperature Tc. Now consider a uniform rod of length L with insulated sides to prevent energy from escaping. If the ends are in contact with two reservoirs at different temperatures, a steady state is reached where the temperature gradient becomes uniform. In this case, the temperature gradient is simply the difference between the hot and cold temperatures divided by the length of the rod. Consequently, the power or rate of conduction is calculated as the thermal conductivity times the area multiplied by the quantity of the hot temperature minus the cold temperature divided by the length. When we deal with compound slabs made of multiple layers in thermal contact, the steady-state rate of energy transfer must be the same through every layer. This allows us to define the R value, which is the thickness of a material divided by its thermal conductivity. For a multi-layered system, the power equals the area times the temperature difference, divided by the sum of the individual R values for each layer. The figure illustrates two materials with different conductivities and thicknesses, where the energy flow remains constant as it passes through the interface temperature denoted as T. In home insulation, the total R value for a wall is simply the sum of the R values of all its individual components. This calculation must also include the stagnant air layers that naturally stick to the interior and exterior surfaces. As seen in the diagrams, a typical wall might consist of brick, sheathing, an airspace, and drywall. If we replace the airspace with a material like fiberglass, which has a much higher R value, we significantly reduce the rate of energy transfer, keeping the home warmer in the winter and cooler in the summer. The second mechanism is convection, which involves energy transfer by the actual movement of a substance. Natural convection is driven by density differences. For example, hot air rises in a toaster because it is less dense than the surrounding cool air. Forced convection occurs when a substance is moved by external means, like a fan or a pump in a heating system. Convection is vital for boiling water, as the warmed lower layers expand and rise to be replaced by cooler, denser water from the top. The third mechanism is radiation, where energy is transferred via electromagnetic waves produced by thermal vibrations. According to Stefan's law, the rate at which an object radiates energy is proportional to the fourth power of its absolute temperature. Specifically, power equals the Stefan-Boltzmann constant multiplied by the surface area, the emissivity of the material, and the temperature raised to the fourth power. The emissivity ranges from 0 to 1, where a value of 1 represents an ideal absorber known as a black body. In reality, objects both radiate energy and absorb it from their surroundings. The net power lost or gained is the Stefan Boltzmann constant times the area and emissivity, multiplied by the difference between the object's temperature to the fourth power and the surrounding temperature to the fourth power. This explains why bridges freeze before roads. They lose energy from both top and bottom surfaces and lack the heat reservoir of the ground. Similarly, frost forms on car tops because they radiate energy to the cold open sky without receiving much back. The Dewar flask is a brilliant application of these concepts, designed to minimize all three types of energy transfer. It features a double-walled glass vessel with a vacuum between the walls to eliminate conduction and convection. The internal surfaces are silvered to reflect radiation and maintain very low emissivity. Finally, the flask has a small neck to reduce energy loss at the opening. This construction is so effective that it is used to store cryogenic liquids like liquid nitrogen and oxygen at extremely low temperatures for long periods. To summarize, thermal conduction involves the exchange of kinetic energy through collisions and depends on the material's conductivity and thickness. Convection is the transfer of energy through the movement of matter, whether natural or forced. Radiation occurs through electromagnetic waves and is highly sensitive to temperature. Effective insulation utilizes materials with high R values to stop conduction, while specialized containers like Dewar flasks combine vacuums and reflective surfaces to block all three modes of transfer. We conclude with a few review questions to test your understanding. First, consider why the physical properties of metals make them good at conducting both heat and electricity. Second, think about a compound wall with two layers of equal thickness. If layer A has A thermal conductivity that is twice as high as layer B, which layer will have the higher R value? Furthermore, how would this difference impact the total rate of energy transfer through the entire wall system? Reflecting on these will help solidify the relationship between conductivity and resistance.